Welcome to lesson number 5. Today we're going to talk about different scales where we see logarithms. Now the first is the Richter scale, which works on a logarithmic scale, and each magnitude on the scale corresponds to a factor of 10 from each level of intensity as we move up or down the scale. So that means if I have a magnitude 9 earthquake, that's going to be 10 times larger than a magnitude 8 earthquake, which is 10 times larger than magnitude 7, which is 10 times larger than magnitude 6. So let's look at some of the examples down here. You can go through and you can read this yourself, but what we want to see is we're also given this scale on the side that gives us the measurements of different earthquakes that hit in different years. All right, so an earthquake of magnitude 8 is, we already know that is 10 times as intense as an earthquake of magnitude 7. So if we go from 7 to 8, what that actually looks like is going from 10 to 8 minus 7, that's just 10 to the 1, which is equal to 10 times. What if I have an earthquake of magnitude 7, and I want to know how many times stronger it is than an earthquake that has a magnitude of 3? Well, I know the difference from 7 to 3, or 3 to 7 is 4, so that would be 10 to the 4. And if we input that, that's 10 times 10 times 10 times 10, or 10,000, which means that an earthquake of magnitude 7 is 10,000 times as intense as an earthquake of magnitude 3. An earthquake of magnitude 4 is going to be not as intense as an earthquake of magnitude 6. So this is going to be 10 to the negative 2, or 1/100th. So we can say that an earthquake of magnitude 4 is 1/100th times as intense as an earthquake of magnitude 6, or 10% as intense. An earthquake of magnitude 4.8 is how many times as intense as an earthquake of magnitude 6.8? Well, again, 4.8 minus 6.8 is 10 to the negative 2, which would again be 1/100th. Now what we're doing is with E and F is we're looking at different earthquake intensities on our Richter scale up top here. And so the first one we're looking at is the earthquake in Chile, and this earthquake was huge, and that measured 9.5 on the Richter scale. And then we have the 1976 earthquake in Italy, which was quite a bit smaller, and this was 6.5 on the Richter scale. So if I want to know the difference between the 1960 earthquake in Chile, that was 1,000 times, so 10 to the 3. So the difference from 9.5 to 6.5 is 3, which means 10 to the 3 would give us 1,000 times as intense as the 1976 earthquake in Italy. But how about if we compare the Italy earthquake to the earthquake in Colombia, which was 5.5 on the Richter scale? Well, and actually, let's see, the 19 was 1,000 times. Oh, sorry, we're comparing the Chile earthquake to the Colombia earthquake. So that's 10 to the power of 4, because the difference from 9.5 to 5.5 is 4. So 10 to the power of 4, we're going to have 10,000 times as intense as the 1983 earthquake in Colombia. And then the 1966 earthquake in Turkey was 6.9 on the Richter scale. And so if that's 6.9, how many times intense was it if we compare it to the 1933 earthquake in Japan, which was also pretty huge? And that was at 8.9. Well, 6.9 to 8.9, and we're going the other way. That's a difference of negative 2. And so 1/100th again. All right, so now we can see that whenever we hear about an earthquake in the news or whatever, if we compare it to other earthquakes of various sizes, we can see how the base 10 system works in just measuring the magnitude of all those earthquakes. So now what we're going to do is compare earthquake intensities. So to compare the earthquakes, the intensities of magnitude M1 and M2, consider the following. The magnitude of an earthquake is given by the formula M is equal to log I over IO, where I is the earthquake intensity and IO is a reference intensity. So we're given an example here in M1 and M2. What we want to do is show that if we subtract M2 from M1, it's going to be equal to the log of the intensity of the first divided by the intensity of the second. Okay, so the first place to begin is with our formula. M1 minus M2 is equal to log I1 over I2. One way we can simplify this is if we separate this log into its individual components. So that would be 1I minus, since we have the quotient law here, minus log to the I2. And if I have I2 over I1, remember that we can also write this, if I'm talking about M1 and M2, log M1, or sorry, M1 can be written as log I1 over IO. And M2 can be written as I2 over IO. So there we've separated them into their individual components, and we're going to do the exact same thing all over again, but this time we're going to use our quotient law. So this is going to become log of I1 minus log of IO minus, and I'm going to separate this into another set of brackets, log of I2 minus log of IO. Alright, now we can, if I get this out of my brackets, I'm going to have to distribute this negative sign into it, just as if we were working with a polynomial here. But I'm going to be left with log I1 minus log of IO minus log of I2. And if I distribute this negative sign, I'm going to be left with plus log of IO. Now the next thing you might notice is that if I have a negative log and a positive log IO, and since those are like terms and they're opposite like terms, I can cancel them out, and I'm just left with these two expressions of log I1 minus log I2, and we can then refer that as log I1 over I2. Okay, so with these earthquake intensities, we could do the exact same thing with this next section, but I'm just going to skip this for now. But with the next question, what we're going to look at is measuring these differences. So in this first example, how many times more intense was the 1960 earthquake in Chile than the 2005 earthquake in Chile? Magnitude 7.8 for the Chilean, the 2005 Chilean one, and 9.5 for the 1960 Chilean earthquake. So if I have I1 over I2, that becomes 9.5 over 7.8. And remember, these are on a base 10, and so what this is actually saying is 10 divided by 9.5 minus 7.8, which means 10 to the 1.7. And if I raise 10 to the 1.7, that's going to be 50.11, and we're rounding to the nearest whole number, so it's going to be 50 times more intense. Now, a major earthquake of magnitude 7.5 is 375 times as intense as a minor earthquake. Find the magnitude to the nearest tenth of the minor earthquake. Alright, so I'm going to use the second formula that we were supposed to look at, but I didn't do that the one step of just breaking it down and showing where it comes from. But we're going to have to use this one here. And what we're going to be left with is I1 over I2 is equal to 10 to the power of M1 minus M2. And that's actually the same thing we did up top, but what we're going to have to do now is just fill in what we have. We know that we already have the intensity, and that's 375 times more intense, right? And the next thing we need to do is solve for, if we know that we know that a major earthquake has the magnitude of 7.5, so that's going to be M1. We want to know what the minor earthquake is, M2. So what we're solving for then is M2, which we'll call X. Now I have an expression that I can turn into log, which will leave me with log 10 of 375 is equal to 7.5 minus X. If I were to switch these around, so X is positive, I'll have 7.5 minus log 10 of 375. So again, all I did was I added X to both sides and subtracted log 10 of 375 from both sides, leaving me with this expression. If we were to put in log 375, we're going to get an answer of 2.5740, but I'm just going to round that for now. And of course, I'm not rounding it until my final answer. And subtract that from 7.5. We're getting an answer of X is equal to 4.92. And we want to go to the nearest tenth, so we're going to say that the magnitude of the minor earthquake is 4.9. All right, so this is just an example of how we use logarithms in order to solve different scale questions, and we're going to look at a few other ones. Next one we're going to look at is the decibel system. Now, the decibel system, it was originally measured in bells, and that was named after Alexander Bell. And the current that we use in the current unit we use in the decibel system is the decibel, which is in dBs, which is equal to 1/10 of a bell. So deci means 10, and then bell was the original unit. So like the Richter scale, the Bell scale is also a logarithmic scale. A difference of 1 bell or 10 decibels corresponds to a factor of 10 in sound intensity. So very similar to the Richter scale. Now, what we have are different on this scale over here. We have different objects and what they register in decibels on this scale. So let's go to the first one. A power saw is at 120 decibels, and it's how many times as loud as a telephone dial tone? Well, if I have 120 decibels, if I look at what the telephone dial tone is, the telephone dial tone is 80 decibels. I know that if I look at like how many bells this is, so 120 decibels, remember 1 bell is equal to 10 decibels. So I have 120 decibels, that's equal to 120 bells. And 80 bells would be decibels, would be 8 bells. Now this is where I calculate using logarithms. If I see which one's louder, obviously the power saw is 12 minus 8 would be equal to 10 to the 4. So that would be 10,000 times as loud as the telephone dial tone. A jet engine is 145 decibels. If we look at how many bells that is, that's 14.5 bells. And if we were to compare to the threshold of pain, which is 125 decibels, or 12.5 bells, that's going to be a difference of 2. So 14.5 minus 12.5 would be 100. So a jet engine is 100 times as loud as the threshold of pain. And then finally a whisper is 30 times or 30 decibels, which would be 3 bells. And a conversation would be 6 bells. And so we're going the opposite direction. We would be left with, if we go 6 minus 3, 10 to the negative 3, we would have 1/1000th. So what we're saying is just how much more quiet is a whisper than a conversation. And in this next section, we're just going to go over how we apply this scale in comparing the loudness of sounds. So let's start off by looking at an example. And there is an equation that we're going to use. It's similar to what we looked at in the last section. But what this tells us is if I have 1 decibel, 1 decibel would equal 10 log I to the O. And again, I is just a measurement of intensity or loudness. And so 1 decibel, we would have 10 log of I over O. And what we're trying to do is show that the decibel level for the threshold of pain has a sound intensity of 10 to the power of 12.5. So if I were to talk about this, remember that this is my bells. So 12.5 is my bells, which means that the decibel will be 125 decibels. And 10 log I the O, since we don't have any of that information yet, I can't exactly use it. What we're just trying to show is that this is equal to this. So now what I'm left with is 10 log I to the O, and I gotta get rid of this 10, right? That's 10 times log to I over the O, and so I gotta divide 125 by this coefficient, which would leave me with 12.5 is equal to log. And remember that if I don't have anything a base in front of after my log, that's just base 10. Now, what I want to do is represent this using exponential form. And so if I were to put this in exponential form, I'm going to be left with 10 to the power of 12.5. And remember, I'm trying to show that it has a sound intensity of 10 to the 12.5 IO. And so if I'm looking for the intensity, I kind of multiply both sides by IO, and that would give me I is equal to 10 to the power of 12.5 times I to the O. So how many times more intense is the sound of a piano playing at 67 decibels than a whisper at 22 decibels? Well, I have I1, and I'm using this formula up top here now, divided by I2, and that's equal to 10 to the power of decibels, so 6.7 minus 2.2, which would equal 10 to the power of 4.5, which would be 31,622, 22 times more intense. And in this next expression, what we're looking for is the total loudness, so the decibels, and what we're gonna have to do is solve for an exponent of x. And if you want, I can show you how to do this next question in class, but I don't want this video to be too long for you, so I'm just gonna keep going. Okay, so the fun one now. We're looking at the pH scale. What we haven't talked about in Chemistry 12 yet is just the chemist who came up with the pH scale, Soren Sorensen. So pretty sweet name. And what he discovered was that if we represent the acidity of something by how much hydrogen it contains. So I've seen this mean the hydrogen potential, but we could also use it to represent the expression the power of hydrogen to measure how wide the range of hydrogen ion is in each substance. Now remember, the pH scale has a range from 0 to 14. Anything above 7 is considered basic or alkaline. Anything below 7 is considered acidic. So again, it's similar to the Richter scale or the decibel scale that we are using a base 10. So a difference in 1 unit of pH will correspond to a factor of 10 in intensity. So if you have an acid that is a pH of 3 and then one that's pH of 4, the pH of 3 is 10 times more acidic than the other acid. So let's look at some examples. So tomato juice. Tomato juice registers as a 4 on the pH scale, and if we compare that to water, which is 7, tomato juice is going to be 10 to the 7 minus 4, or 10 to the 3 times more acidic, which is 1,000 times as acidic as pure water. Eggs, if we were looking at how much more eggs are alkaline than pure water, then eggs has a pH of 8, and water we know has a pH of 10. That's only a difference of 1, so 10 to the 1 would be 100 times as alkaline as pure water. Milk of magnesia is at a 10.5, whereas blood, when it's alkaline, is at 7.5. That's the difference of 3. So that's going to be 1,000 times as, and since it's more basic, it's more alkaline, or basic as blood. Vinegar is the next one, but if we have normal range, pH of 5, and we want to see what is 100 times as acidic as that, well, we have to look at what would give us a power of 2, and the only thing is going to be 5 minus 3, which is vinegar, and that will be 100 times more acidic. And then if we look at the eggs and compare the eggs to the washing soda, eggs again have a pH of 8, and the washing soda has a pH of 12. And so that's going to be 10 to the negative 4, which would be 1 over 10,000. Now the next question, we're comparing acidity. Now to compare acidity, we use this formula. And I'm just going to do class example 10 here. To compare acidity, we use pH is equal to the negative log of the concentration of hydrogen ions that we have. And let's see, in this question, a patient gave a urine sample that was found to have a pH of 5.7. So pH is equal to negative log of the concentration of my hydrogen ions, and I know what my pH is. It's 5.7, and negative log, we don't like working with negative log, so we'll bring the negative sign over here. Just divide both sides by the negative, and we're left with the log of H plus. And now what I want to do is I want to make this, remember this is base 10, and so I want to make this into exponential form, which would give me, H plus is equal to 10 to the power of negative 5.7. And so if we're looking at the concentration of the hydrogen ions is going to be equal to 10 to the power of negative 5.7, that's going to tell us what the concentration of the hydrogen ions actually are. And I got 1.99 times 10 to the negative 6, which we would round to the nearest one decimal place, so 2.0 times 10 to the negative 6. And if we're talking about concentration, that's going to be in molarity.